the CE lab. What time is it, Brandon?
It's 2:48 a.m.
On
March 19th.
March 19th. And our project actually works. It is a true miracle. And here it is. And here's the oscilloscope.
Let's get a good view of all those.
Ooh, look at those strobes.
Yes, the strobe.
All right.
Controlled by our code.
So, let's compile. Did you already debug?
Here we go.
Let's debug. See, this is code we wrote.
Yes.
Oh, and it is ready to resume.
Okay, well, quick explanation how we used a program to automatically click certain places so that we can send frequency pulses. Go to the screen. We are going to be using 2.5 kilohertz and 400 hertz to be sending bits of 1 and 0 to the LPC to decode that will be outputted on UART, on the desktop computer.
And 400 hertz represents a 1.
Yes.
And 2.5 kHz is a 0.
Yes.
So when one of these strobes high, right?
Strobe's low. When strobe is low.
Oh no, sorry. When the frequency goes high, this one will output a 1, whereas 2.5 will output a 0.
Yes.
And all right, let's see some magic happen.
I've programmed it so that pressing the down arrow will activate a 0 pulse, a pulse of 2.5 kilohertz, while as the up arrow is programmed to output a pulse of 400 hertz.
So also this is called frequency shift keying.
Yes.
Well, binary frequency shift keying.
To be specific. All right.
And we paid $5 for the functionality of being able to program the mouse like this.
So I press 1 or I press down and we get a 0 bit, and the UART says both the magnitudes of the 400 hertz reading and the 2.5 kilohertz measurement. The threshold is 4,000, so we see that, and when we input 2 more characters, after the 3rd character, we decode the values as basically a decimal.
That's 3, by the way.
Sum of all of them. Exactly.
Yeah, so this is base functionality. It'll look a lot better during the demo.
1, 0, 0, 1. It's just 1.
Yep, and we're tapping here, tap away, tap to something, and stuff appears. And let's take a look at our waveforms.
Right.
So
I'm tapping the down arrow. We see the fifth column. That is the 2.5 kilohertz bin that the chip is decoding. We see it spike, and we see the decay over time.
It has a 10% decay rate, apparently.
Yes. And when I press up, we see the 1 bit transmitted through the 400 hertz bin, also showing the decay.
And we can process these signals a lot faster, but for our purposes, we made the delay pretty significant.
The strobe period is high so that we can fully charge.
Yeah,
and get those clean squares.
This
at the top.
blue line at the bottom is the strobe, and it's active low. All right, I think that's proof enough that it works. And oh look, we hooked up some stuff up here as well.
Right, we're utilizing 2 GPIOs to serve as output from the LPC. We are outputting the strobe and the reset signals to the MSGEQ7 chip. And another pin on the LPC takes in analog input. That is the MSGEQ7's output that the LPC takes in, goes through the ADC, and gives us our values. We are powering the MSGEQ7 chip through an external power source.
Which is
at 3.3
actually
volts.
unnecessary, and we'll
Yeah.
probably switch our power source to the LPC
Yes.
when we finally actually demo this piece
And
of crap.
we are using this cable to transmit the audio from my laptop to the chip,
Just like magic. Just
and
like magic.
UART goes to the computer so that it's easier
That
to
has
see.
termite because
Termite, yes.
for some reason
UART on Mac is
disgusting.
unreasonable.
How do you feel, Brandon? How do you feel? Tell me.
Tired.
Tired?
How do you feel?
We have 2 finals tomorrow.
See the cameraman, camerawoman.
I want to go sleep and take a shower. And oh wait, the final piece of art that has been done in this lab. My Minnie Mouse drawing.
Lovely.
And the end.
Yay.